Welcome. Welcome to the existential crisis room. I'm kidding. But you did all subconsciously sign that in your waiver when you walked in. I'm kidding. Anyways, this is a presentation called Cosmic Wonder about the book of the same name. And um, in case it wasn't introduced, my name is Nathan Hellner-Mestelman, and I have been a rather long-standing, I don't know, member of the Royal Astronomical Society of Canada. I've loved this place, and it's been my astronomy geek out home since I was 10, so the past 7 years at this point. And this is sort of a story and a book that I've written about a cosmic perspective, my love of the universe, and sort of its relation with humanity. And I want to begin this by just talking about how this began, the backstory, so to speak. I've loved the universe for a long time, but it really started when I asked, what's up? In the deeper sense. You can use it for small talk, which I've never been excellent at, or you could use it to ask, what's in there, what's out there in the universe? And my real obsession with the cosmic perspective of sorts began when I was around 12, seeing a total lunar eclipse. And for those of you who don't know, a total lunar eclipse happens when the moon passes directly into the Earth's shadow. So it's like the Earth obscures the sun from the moon's point of view. It's like a solar eclipse from the moon's perspective. And we were watching one of these when I was, I believe I was, I would have been 12, and it was 2019. And I was watching it with a friend across the street from my house, and we were watching the moon, and I decided I was going to take a break because I was hungry. So I was just leaving the telescope, going to get a cookie to eat, grabbing the cookie, and in the 1 minute that I wasn't watching the lunar eclipse, my friend had returned around and it's like, "Whoa, did you see that?" No, because I was eating a cookie at the time. But what my friend had seen was a small flash on the moon's surface, blink of an eye, gone. And I didn't think much of it until the next morning came, and right across the news headlines was "Asteroid impacts the moon during total lunar eclipse." And I had been eating a cookie at the time. But as it turns out, I wasn't alone. About 99.9996% of the world's population didn't see it. It was just a few hundred people, actually, and a few cameras that happened to be pointed at the moon at the time. But some scientific studies were done on this rock, and it turns out it was moving at over 17,000 meters per second, which means it released the energy of 55,000 kilograms of TNT, and it produced a crater large enough to level a city block had it impacted the Earth. And this just blew my mind, blew my little 12-year-old mind in a sense that cannot really be described in words, but it kind of made me think, if that thing had leveled a city block had it hit the Earth, we kind of would have heard about that. But because it hit the moon, all that we saw was a tiny flash. And not only did we just see a flash, most of us missed it because we were eating cookies at the time. And but the point is, it just made me realize so much is happening out there in the universe that we are not present for. We are trapped on this little planet. We are all citizens of Earth. For half the time, we can't even see the stars because there is a cordial blue blanket of oxygen above our heads that obscures it. And the point is, a lot is happening out there in the universe. Just to get you in that mindset, let's do a little experiment. Let's just do some yoga. Deep breaths, 3 seconds in, 3 seconds out. And in the time it took you to do that yoga breath, if we extend that across the universe, here's a few stats on what just happened while you were breathing. Stuff happens, you know? Our universe, the amount of volume, the amount of new space that was just created in our universe during that breath, that's enough to fit our entire observable universe's matter if you crammed it in trillions of times over. There's more space than we know what to do with in our universe. But the point is, so much is happening that I wanted to document all of that existential crisis, mind-blowing, inducing stuff into a book. And this is not what I'm here to talk to you tonight about, but I will be including a short advertisement about it at the end. What I want to address with you tonight with is 3 fundamental questions that are central to this book, but also just really interesting things to ponder in astronomy. These are, where are we in the universe? Where are we from in the cosmos? And where are we going in the big picture? First off, where are we? The question, where are we, is a very difficult thing to pin down, literally because unlike Google Maps, you can't drop a pin. the universe is static. It's not sorry, it's not static. It is always changing. I'm gonna just go off the mic for a bit. This is where we are right now. No, it's not. This is where I'm holding the globe right now. But just imagine that this is where we are. The Earth is already turning at 380 meters per second, which means we are being flung along faster than a supersonic jet just around the Earth's equator. And the Earth itself is moving at 30 kilometers every second in its orbit around the sun. And that means that we are already moving the width of our entire planet in just 7 minutes around the sun. But the solar system itself is moving around the galaxy at 200 kilometers per second, along with 200 billion other stars, and our galaxy is being hurled through the universe at 600 kilometers every second. That's fast enough to cross the width of our entire planet in 20 seconds. And this is the reason why it so sucks that Air Miles and Aeroplan and all those airline companies measured their points by kilometers flown over the Earth's surface. If they only measured it by galactic meters traveled, then we would be earning a free trip to Paris every 7 seconds. But alas, they don't. And this chart here is just a measure of how fast the Earth is moving, like how far it travels every time you do ordinary earthly activities. So we're moving very fast. But we're not moving that fast compared to the fastest speed in the universe. The speed of light is like the compass for measuring where you are in the universe, because light is the same everywhere. It always travels at 300,000 kilometers every second. So fast that if you took a joyride on a light beam, you could reach the moon and back in just 3 seconds. You travel around the planet in 1/7 of a second. How's that for world travel? It's not even the Aeroplan 7 seconds to Paris. But basically, the point is, light is a universal constant, which means even though it's fast, it does take time for light to travel from this point to this point to this point. It takes time for light to travel places. So sound is a good kind of example of like how light behaves. If I shouted, "Buy my book, please," it would take around 1/100th of a second for those sound waves to go from me to you guys. So even if I shouted, "Buy my book, please," now, you wouldn't actually hear it for 10 milliseconds or 100th of a second, which means, for all you know, I said that 100th of a second in the past. Whereas if I waved my book back and forth in a very advertising manner, the light travels like a sound wave out in all directions. It's a lot faster than sound, because it's a universal constant, but it still takes 10 billionths of a second for the light of this book to reach you, which means you're actually seeing me doing this 10 billionths of a second in the past, because there's a delay between when I do it and when you see it. And that's basically instant for us here on Earth. But across the universe, it adds up. Across the solar system, it takes 10 hours for light to travel from one end of Neptune's orbit to the other end, which means if you were standing on one side of Neptune's orbit and you were watching the other side of Neptune's orbit, you would be seeing it 10 hours in the past, because whatever happens on this side, that side won't know about it for 10 hours. And whatever happens on that side, this side won't know about it for 10 hours. And our galaxy is so much bigger than that. It's so large, it takes 100,000 years for light to travel from one side to the other. 100 millennia. You know, an interesting fact is that human civilization has only existed for around 12,000 years, which means in the entire time that humanity has existed as a civilized species, light has only traveled that far. All documentation that we exist here as a civilization has only traveled that far into the universe. And you ask, why haven't we discovered alien life yet? Maybe because our texting range is a little bit limited right now. That, compared to the observable universe, is like trying to scan the oceans to see if there's fish in them, but using a swimming pool as your reference. And it's really kind of sad how little our light has traveled into the universe, because the Milky Way is one of several hundred galaxies in a group of galaxies called the local group. Is called the local group. It's 10 million light years across. It takes 10 million years for light to cross one end to the other. Like when I think local, Local neighborhood, that's like the few houses around you. Astronomers, when they think local, they think 10 million light years. I don't know what it is with these guys, but you know, it's a matter of relativity, what can I say? And the local group is one of about 100 groups in a cluster called the Laniakea supercluster, of which our local group is a part. It's around 520 million light years across, so it takes 500 million years for light to get from one end to the other. That means if you stood on, like down here, somewhere in this galaxy down here, and you looked all the way back to our Milky Way, and you somehow had the absurd magnification and expensive camera equipment to zoom all the way into Earth, you would be seeing light that left Earth 500 million years ago. You'd see the Earth 500 million years in the past, which means, what would that be? The Cambrian explosion, where multicellular life was first evolving? Like humans would not even be a idea yet in like terms of evolutionary history. And it turns out the Laniakea supercluster is one of around 10 million superclusters in the observable universe, which spans around 93 billion light years from end to end. And turns out that this is just an optical illusion. It's not even the edge of the universe. I know we say observable universe, it has like this sort of boundary, but remember, the further back in space you go, the further back in time you're looking. And it just so happens that there's only so much time you can look back on, because our universe is 13.8 billion years old since the Big Bang. And if you look back more than 13.8 billion light years worth of space, and then when you account for the expansion that's happened since then, it stretches to that number, it kind of, you're looking right back to the beginning of time itself. And that leaves you with no more space left to look. So because the further in space you look, the further back in time you're looking, you're kind of out of room at a certain point because you've hit the beginning of time. But that doesn't mean that stuff doesn't exist beyond it. It just exists so far away that light has not had time to reach us in the entire history of the universe. I like to use this illustration. If this is us right here, we can see this far in all directions. This is our observable universe. At this point, we've reached the edge of time. We can't see beyond it. We see some galaxies right at the edge. From their point of view, we're right at the edge of their observable universe. And then they get this whole bonus section that we very sadly will never, ever get to see. Not because we don't have good enough telescopes, but because it is fundamentally off limits based on the speed limit of our universe, the speed of light. And I feel like we've done kind of a better job nullifying the question, where are we, than actually solving it. Like, where are we? In the middle of an infinite expanse of space, where up and down carry no meaning whatsoever? That's where we are. Helpful? Not so much. But anyways, that's all I can provide you with, unfortunately. The second question, where are we from, stems from a very basic childhood question that I asked when I was a little kid, and many of you may have as well. It's, where do babies come from? We can talk about the parents, sure, but that's hardly cosmic. I mean, you talk about the grandparents, the great-grandparents, you trace it all the way back, you end up with something that looks a bit like this, the evolutionary tree of life. And this is more or less where babies come from. And it turns out we're all kind of related. We're from the same species. You know, if you take the more mathematical approach of like tracing generations, you could say, okay, first of all, you have to simplify kids to like data points, which kind of sucks, but you take this one point, connect it to two other points, those are the parents, you connect those 2 points to 4 points, those are the grandparents, and then the great-grandparents, there's 8 points, and then there's 16 points for the great-great-grandparents, and it turns out you build this sort of tree, mathematical tree, but of course, you don't just have your own tree, your tree kind of merges with the trees of everyone else. That's why we have siblings, cousins, second cousins, third cousins, and so on. We all kind of merge in our heritage. And it turns out that when you merge these trees like this, you can calculate that within calculable error, it is almost certain that within the last 3,400 years, you and me, like no matter who you are, you and me shared a common ancestor, at least one. So you, we have at least one common ancestor within the last 3,400 years. And that means we're all 50th cousins or closer. Family reunion, everyone. And if you extend it back even further, turns out all humans actually share 99.93% of their genetic code. And humans and chimpanzees share 98%, and humans and wolves share 80%. Humans and mosquitoes, even mosquitoes who you may have mercilessly killed on your wall to give you more like restful nights, that was 60% your genetic brethren right there. And it turns out you trace this all the way back to the beginning of life, and you find this guy named Luca. That was the cell's name that kickstarted life around 4 billion years ago. Luca actually stands for last universal common ancestor, but Luca's a cute name, you know? And one of the leading theories about how this happened is you have these very, very small molecules called RNA. I mean, we all know the DNA in our cells. This is like half of that. Like you unzip DNA, you get a strand of RNA. So this RNA floating through the ocean, RNA knows how to program for molecules, but it really can't copy itself. Then there's another type of molecule floating through the ocean called proteins. And like literally the same kind in your protein bars, but just floating through the ocean. Proteins know how to copy RNA, but they can't copy themselves. So at some point, there's this very sweet romance between two molecules where a strand of RNA meets a protein, they bind together, the protein knows how to copy the RNA, and the RNA knows how to program for the creation of the protein that knows how to copy it. So in a very loop-like fashion, you've created a machine that knows how to copy itself. And that sort of romance between RNA and proteins persists to this day. You know how like when you drop like oil in water, it kind of forms these bubbles because oil does not like water. And oil tends to resist water and bubbles up. If you imagine something like that happening with acid at the bottom of the ocean, you get these little bubbles. And if one of these RNA protein romances is going on inside these bubbles, you've created a cell. Congratulations. And it just so happens that this RNA protein romance is still going on inside all of our cells today. You cannot build proteins with little strands of RNA in our cells. So we all contain replicated fossils of Luca. Luca lives on in all of us. And that's very sweet, I think. But where did Luca come from? Because where did Luca come from is just an extension of the question, where do babies come from? We haven't finished answering that yet. Well, it turns out the Big Bang kind of created a very uniform smoothie in our universe. Just hydrogen and helium. It was very boring. You couldn't do much with that. Stars formed out of that, and they were so energetic that in their cores, when they blew up, they smashed hydrogen and helium together into a whole bunch of other ingredients that were later used for life, the universe, and everything, to quote Hitchhiker's Guide. Yes! Like lead, oxygen, gold, titanium, carbon, iron, all the stuff that you find around you, everything in your body, everything in this room, everything that isn't hydrogen and helium was cooked in the core of a star billions of years ago. And if you take it all the way back, you find that everything in our universe can be traced back to a few particles appearing when the universe was about this big. So imagine the universe just a fraction of a second after the Big Bang when it was this big, and a few particles appear. Just like out of the blue, out of the energy of the universe. You get some particles, and then they disappear. And in doing so, they leave little particle fingerprints, like subatomic tiny fingerprints, dents, marks in our early universe. And then the universe explodes violently and grows to galactic scale. And in doing so, it stretches those little subatomic fingerprints to the size of galaxies. And it leaves all this empty space left over for matter to flow into. It's kind of like if the Earth were this big and I left some little fingerprints in it, and then I expanded it to the size of the Earth, those fingerprints would be the size of continents, and if you poured water on it, all the oceans would flow into my fingerprints, even though my finger alone couldn't create an ocean. It took a huge expansion. But these particles did the same thing. They left tiny little particle fingerprints in our early universe. Then the universe grew to the size of galaxies, and then matter and energy and stars flowed in and filled those little spaces. So every little bit of structure you see in the universe today, you can owe that to just a few hundred particles right after the Big Bang. Another thing that appeared right after the Big Bang was a whole bunch of gamma radiation. This is the nastiest kind of light in the universe. It will destroy your DNA. But don't worry, because all that gamma radiation released after the Big Bang has cooled down so much that it has softened a bit into microwave radiation. I still wouldn't recommend you step inside a microwave, but it's a lot less energetic than gamma rays. And I'm going to come back to that microwave radiation in a little bit. But just for now, just know that that microwave radiation is still all around us, left over from the Big Bang. And that's where babies come from, in the biggest sense. And the last question, where are we going? This is like the kind of depressing one, but don't worry, it gets better in a bit. And basically, where are we going is kind of like asking, what is the cosmic doomsday? The idea of a doomsday is certainly nothing new. I mean, if you added it up from all the world's major religions, the world was actually scheduled to end around 200 times by now. It hasn't yet, but the universe does have an expiry date, sadly. And it all has to do with an epic cosmic battle between two cosmic forces. The first, gravity. Gravity pulls things down. I would rather you didn't do that to my book, but if you choose to get one, but you can if you want. And gravity, it pulls things together, pulls galaxies together, it pulls planets around the stars they orbit, it pulls stars around the galaxies that they spin around, it pulls our planet together, it pulls us down towards the Earth. It pulls everything together. The ultimate enemy of gravity is dark energy. We don't know a whole lot about this yet, but dark energy seems to be pushing space apart in all directions. Pushes galaxy clusters apart, pushes our universe apart. And so the question is, in the big picture, will gravity win or will dark energy win? Or will they just tie? Will they balance out? I hope for the last one, because as you'll soon see, neither of the first two options are pretty. The first possibility is that gravity wins, that all the expansion that's been happening in our universe was for naught. And it all gets undone by gravity pulling things back together. So eventually the galaxies start pulling themselves together, the stars start pulling themselves together, and the whole universe slowly contracts until everything in the cosmos has a nice big hug. A really sweet, romantic hug. And collapses into a cosmic singularity, basically turning everything into a black hole, in which case we kind of die, but not for billions of years, don't worry. And the exciting possibility about this is there's a chance that when the universe collapses, it actually rebounds into a whole new universe, kind of like dropping a bouncy ball on the ground and then it coming back up again. And that is called the Big Bounce theory. And it could actually have been what created our universe. We could have been created from the total collapse of another universe before us. And that kind of is like just an endless sort of cycle. What's not so endless is the second and far worse possibility that dark energy actually wins. This is one of the least likely possibilities, but it is still a possibility. It has not been scientifically ruled out. And what happens if dark energy wins and chooses is able to accelerate the universe apart is that everything that is currently held towards by gravity, everything in the universe that is held together by gravity will kind of stop being held together by gravity. And since I kind of like being on this planet held by gravity, that's not a good sign for everything. So the first thing that will happen is that galaxy clusters drift apart. Then galaxies with their spiral whirlpools of stars will begin to drift apart. Then the planets orbiting stars will begin to spiral out. Our Earth will be pulled away from the sun in like billions of years, remember. And it's quite possible that the sun will have already kind of done its thing and exploded by then. But regardless, this is really pessimistic, I'm sorry. I'll promise I will make it happier in the end. But in the end, in this scenario, atoms get ripped apart, particles get ripped apart, our planet crumbles like a dry cookie in all directions and gets ripped apart. And in the end, everything gets spread infinitely thin as space expands to infinity. In which case, we also kind of die. The third and much more likely possibility, and my favorite, is that dark energy and gravity just call a truce and they balance out. And current theories predict that gravity and dark energy actually will equal each other in the end. And that means that our universe will keep growing at a steady pace, nothing dramatic will happen, stars will fade away, galaxies will disperse. And just to point out, we still die in this case. But it's a nicer death. And you know why? because we have trillions and trillions of years before it happens, unlike the other two scenarios. One of the first things that will happen is that our sun will run out of fuel and will begin to expand, and it will kind of consume Mercury and Venus and eventually the Earth. So if you're going to be around in 5 billion years, pack sunscreen, because not only will you be hanging out tanning in the sunshine, you can drop the shine because you will be tanning in the sun. And so after that, the sun will leave behind a little white dwarf star, like an ember of a once glorious fire. And that will kind of slowly fade away over trillions and trillions of years, which we will probably have technology advanced enough to escape that if we're still around by then. So fret not. What you should fret about is something that happens a trillion times further into the future, which is that protons, one of the fundamental building blocks of all matter, might be unstable and have a half-life. And that's just a fancy way of saying, warning, could explode without warning. And that means that unimaginably far in the future, this is like a 1 followed by 33 zeros, years into the future, protons may just fall apart. And like Avengers Endgame, we might just slowly turn to dust. And that's not a great thing if you like your matter, because I do. And but the good news is there will be nothing left by this point anyways. And then the real end game, which is that even black holes, which is something that astronomers for many years thought were invincible, indestructible. Turns out they emit a small trickle of radiation that eventually leads to them decreasing in energy, losing mass, and eventually they just wither away to nothing. That will be in around 10 to the power of 106 years, which is a 1 followed by 106 zeros years from now. There was a project I did about 1.5 years ago where I kind of attempted to calculate the end of the universe. It was a phase, oh God. But the point is, well, I had a lot of generous help from folks at the Royal Astronomical Society who were able to take pictures of distant supernova explosions with the SLU Observatory in Australia. And you know how like the faster the universe is expanding, the further back in space you look, the further back in time you look. So if you're taking pictures of distant galaxies, you're kind of capturing snapshots of the universe as it looked in the past. And then you can measure like, how was it expanding in the past? How is it expanding now? Extend. How will it expand in the future? And we did figure out roughly when the universe is going to end. It turns out when you take all the stars, all the galaxies, all the life that will ever exist in the universe, and you turn that into like a time zone, 100 trillion years of glorious starlight and galaxies and a chance for us to prosper. 100 trillion years. That golden age is this much of our universe's entire lifespan. There is a long, long road ahead of us. And then, of course, the little kids came in to check out the science fair. And I was like, oh, great, I have to explain this to little kids. Like, our universe is going to die, everyone's going to die. Oh, but then it struck me that these kids were just here to learn things. They're just curious. They don't carry the existential dread that us teenagers have to deal with. Like, they are the ultimate scientists, I think. Little kids in the room, it's just curiosity. It's just a desire to know. It's not trying to depress you or anything. And by the way, I'm not going to be depressing in the next slide. And but the point is, I think that this number, stepping away from the mathematics of it all, really helps us appreciate the moment, because never again will the universe look as good as it does right now. Everything is always tending towards disorder and disarray, and your room is, and certainly not mine, is not the only example of that. Stars burn out, galaxies disintegrate, but we happen to live in that fraction of our universe's lifespan where life is possible in the first place. And I'm so glad that I get to spend this night with you guys in this little fraction of cosmic time we have to even contemplate the universe. And that brings me to my last slide. Why tell this story? A little bit of geopolitics first, then the optimistic part. We live in a very, very complicated era of human history. We kind of seem to be disagreeing across political factions over the most basic fundamental human truths. We have divided up the Earth's landmass on borders that don't actually exist. They're just lines on a map. We are polluting the atmosphere. Climate change is rampant. And to top it off, we have 30,000 unused nuclear warheads that we haven't quite figured out what to do with yet. But astronomy, as Carl Sagan put it, is not just a body of knowledge, it's a way of thinking. Because when you think in the language of astronomy and the perspective that it brings, then suddenly all of this chaos is something that's happening right there. I mean, not there because that's just my own drawing, but like on a small blue marble that is careening through the cosmos at absurd speeds, that is so fragile and so small in a universe that is so unimaginably large, it wouldn't change one bit if we just pressed delete on that planet. But I would rather we didn't do that. And it has saddened me, some of the actions that our species has just take in the absence of that view, that this is all we got. We currently are spending as a species on a global level $2.45 trillion every year on military arms development. You know what else would cost about that much amount of money? Taking all the political and military leaders in the world and just giving them a short trip to space on a rocket to see that. Because all the wars that have ever been fought across human history have been done by humans. And in every human is a mindset that drives that sort of action. And so if you are willing to spend money to promote the mindset of destruction, you might as well spend that money to create a mindset that fosters this kind of image. And the people who are running our planets maybe could use something like that in the near future. And this is one of the first times in human history that we have actually been able to contemplate this, because we have the technology, we have the means, we have the knowledge. And so I'm really grateful to have been able to share this with you tonight. Now, the optimistic bit. It is more a testament to curiosity. There is so much just waiting to be known in our universe, all around you. The universe isn't just out there, it's all around us. And this is where I want to talk about that microwave radiation that the Big Bang produced 13.8 billion years ago, right after the Big Bang. What I want you to do, for those of you who came here in a car, I want you to turn on your car's radio on the way back home. And I want you to, instead of tuning to like Sirius XM radio or like Kiss 103.1 or something like that, I want you to tune it to no radio channel. Just some random number that isn't booked by any broadcasting station. And I want you to just listen to, because you know what that is? That is the microwave radiation left over from the Big Bang. When you're not listening to any radio channel, you are listening to Cosmic Jazz, the first music album ever broadcast 13.8 billion years ago. So if that just serves as an inkling of curiosity to pique your interest after tonight's, you are free to do that. And I think as long as we keep looking up as a species, as long as we keep expanding our worldview, expanding what we conceptualize as possible, as long as we keep innovating and staying curious, then I think it is not fair to call it the end. But it is the end of my presentation. So thank you so much for coming tonight. And if you have any questions, I would be more than happy to take them. Any questions about life, the universe, and everything? 42. Yes. I'm excited to see where AI goes. Here's an unsettling thought, if that wasn't already. It's all good. Yeah, there's a lot you can do with a double-edged sword like AI. I sincerely hope for the betterment of us all that you choose to be on the pro-humanity side of the development of artificial intelligence. Just a humble request. You can do whatever you want, you know, it's your future, your life, what can I say? Yes. This was a 2-year-long project, and yeah, it's been my passion project and my joy to compose this over the last 2 years. Yes, I think that as long as we have the benefit of the doubt that it has not been conclusively proven that aliens don't exist, I think it is almost inevitable that some form of life does exist across the cosmos. You have at least one planet on average around stars, just generally. You have 200 billion stars in our galaxy. You have 2 trillion galaxies in the observable universe. That adds up to more planets than there are grains of sand in the Sahara Desert. So it's a lot of worlds out there. And I think there's another fact, if you don't mind the ramble, that kind of just really solidified that opinion in my mind, which is across evolutionary history, wings, every creature that flies, wings evolved 4 different times. It wasn't just that wings evolved once and then gave birth to descendants. Wings evolved 4 separate times over the Earth's history, completely disconnected from one another. Photosynthesis, the green plants drinking light, that evolved 40 times, 40, across Earth's evolutionary history. And eyes, the ability to see, evolved 65 times, with no assistance or help from any other species that already saw, just on its own. And I think if traits are that universal across completely disconnected regions on just one planet, I think it's not only possible that life could exist elsewhere in the universe, but it might have features that are not so different from ones that we encounter here on this planet. Anyway, that's my ramble, sorry.
Thank you for taking over here. I was supposed to come in and introduce him.
Oh yeah, this can serve as the introduction to the book. There's the self-indulgent aspect.
We've got some books here. So if anybody is interested, did you introduce yourself?
I did.
All right. I'm glad you did. Because did you tell them that you've been here for since you were 10?
I have been here for a while, and
he started doing observing and different kinds of research when he was 11. And then at 12, he was doing his own project. And by that time, we just let him go. Everyone's anyway. Thank you very much for coming up and talking with us today. It's been an absolute pleasure to have you as always. If you would like, if you are interested, you can have some. There are some books at the back here that are or front, and Nathan will be happy to sign anything for you or answer any other questions that you have. And knowing Nathan, he'll still be here at 11. Anyway, for your information, there is going to be a dome tour at 10 o'clock. And it will. I think they'll open up the telescope for sure. And